In this video, we are going to talk about only one thing, the material coordinate system. Now, this is very important when you want to define a composite in MSC Nastran. So you do this via maybe PCOMP or PCOMPG. But before that, you need to know what a material coordinate system is. Here in Apex, I've already built a very simple model. This model is fixed here on the left, and there's a point load here in the bottom right-hand corner. I purposely used triangular elements, and I'll explain why in a moment. And this whole panel is composed of a composite. So if I open my stack here, it's composed of the following layers: 45, negative 45, 0, 90, and symmetric. Now, here I've already exported the bulk data file, and let's go ahead and make sure that I get results here. Here, I want to make sure that this analysis went through successfully, so I'm going to look for user fatal message. Okay, looking good. Let me make sure I have external work. Okay, perfect. So I do get external work. Now, let's talk about the material coordinate system. Right now, what you see are the so-called element coordinate systems, or before that, let me talk about what a material coordinate system is. Okay, so let's suppose you have an observer like this. You told the observer, hey, my stiffness for E1 is this. It's maybe 100. And then let me make this a little larger. The stiffness for E2 for this orthotropic layer is 200. You tell this person, the observer, these are my values. But then the observer is going to come back at you and say, hey, what's the orientation? Do you want E1 to be in this direction? Do you want E2 to be in this direction? Or do you want E1 to be in this direction? So what's the direction of E1, E, and E2? So this is where we talk about the material coordinate system. So each element is going to have what's called a material coordinate system. And we don't know what that is yet. So maybe this direction would be the X material direction. And this was an arrow here. This direction is the Y axes of the material coordinate system. And then if you use the right-hand rule, this would be the ZM, if you will. But just so we don't get confused, I'm not going to draw it here. Okay, so these material coordinate systems are very important. Each element is going to have its own material coordinate system. So here, let's draw it here. This is a XM and then YM. And then this one could be something completely different. This could be XM and this could be YM. So the point I'm making here is that if you're not careful, and in most cases, in very rare simple cases, or rather in most cases, the material coordinate system is going to be in completely different directions, and I'll explain why in a moment. So it's important for you to know this, because if you don't know this, you're going to incorrectly define your composite laminate. Now, it's in the Y axis of the material coordinate system that defines the so-called 0-degree direction. Now, this is a problem because if each material coordinate system is different, guess what? All your 0-degree directions are going to be completely wrong. And here, I'll show you an example. So here, let's take a screenshot of this. By default, the material coordinate system is parallel to the element coordinate system. Right now, what we're looking at is the element coordinate system for each element. But we know by default, the material coordinate system is parallel to the element coordinate system. So here, let me see what's the best way of doing this. So for this top corner element here on the top right, Oh, that's not a good color. I guess I'll have to use red. This is going to be my X element coordinate system, and this is going to be my Y axis of the material coordinate system. But now we have a problem. Let's pick this element here. This is the Y or XM, and this is the YM. So guess what's happening now? This is your 0 degree direction. This is your 0 degree direction. So guess what? You're defining laminates in completely different directions. Your apply stresses are going to be pointing in completely different directions. That is bad. So now let's go here and let me show you one example here. So let's go ahead and look at some apply stresses. So let's look here. I'm using this tool because this tool does show you the direction for the apply stresses. So let's go ahead and go here. Let's look at maybe the apply stress here, and oh, interesting. We get outer plane. I won't worry about that. Okay, let's look at some stresses here. Let's look at maybe this layer. Okay. So right now what we're looking at is the stress in the one direction for the first layer. And let's go ahead and look at what the angle was. Actually here. Let's jump out of this real quick. Let's orient ourselves with this example. So let me turn on the plies. And let's zoom in. This is a very small and thin laminate. So let's color these. So here at the top and bottom I have 45, then negative 45, 0, then 90. Up here, layer 3, that's a 0 degree layer. So that's the layer I want to talk about for now at least. So let's talk about layer 3 when it comes to the results. Let's select layer 3. Can you guess the direction of the one axis for this layer? Here we'll turn on the display directions option. So for this element, the stress in the one direction is in the vertical direction. For this next element here, this is the one direction. This is the 0 degree direction, if you will. That stress is going in this direction. You can see that the apply stresses are going in completely different directions. My 0 degree direction is in completely different directions. So this is the 45 degree example, negative 45, 0, I believe, 90. So this is not good. Because we didn't tell our observer, hey, this is the 0 degree direction for the stiffness and the stresses, it's giving me completely wrong values. So if you're a new user, this is most likely happening to you. If you've never heard of the material coordinate system, I can guarantee this is happening to you. So now we are going to fix this in this quick video. What do we do here? Number 1, let's create a coordinate system. Oh, accidentally entered the transform tool here. If you look at the right side, we can create coordinate systems. Let me turn off the material coordinate system for now. Okay, let's just go ahead and create one maybe at, well, for now, let's leave the coordinate system as is. We'll click here, and let's go ahead and say we want to create our material coordinate system at negative 10 maybe, or negative 1. Let's see what that looks like. Okay, perfect. So let's commit that. And let's create a second coordinate system. Maybe I'll rotate that maybe 45 degrees. And then this will be at maybe 1, 1, 0. And we'll commit that. Okay, now let's see if this will work. I haven't tried it, but we'll see if it works. Let me delete the old composite and let me recreate this. Let me create, or actually, what am I doing? Let me see if I can undo that. Okay, yep, that worked. Remember, right now, the material coordinate systems are parallel to the element coordinate system. That's not good for us. That means their stiffness, our apply stresses, they're completely different when you go from element to element. This is not okay. What I'm going to do now is the following. I'm going to say, hey, take all the material coordinate systems, force them to be parallel to the axes of this coordinate system here. Force them to be parallel to the x-axis of this local coordinate system. So let's do that real quick. So here in the attribution section, click on material orientation field. Well, here I'm using face, the face selector here. You'll most likely want to use, or actually in your case, you'll most likely want to use the faces option also. Here I'm going to say, hey, take every element associated with this face, force those material coordinate systems to be parallel to the x-axis of this local coordinate system. So I'll select this coordinate system, and the action is done automatically. Let me turn off the element coordinate systems now. Now, I think in this older version, I have to exit the tool, then come back to it, so I can look at the material coordinate system. And look at that. Now I have all the material coordinate systems are aligned with one another. This is the 0 degree direction for each element now. I can now define my laminate, and I know that the stiffnesses are all pointed in a consistent manner for each element. Now here, I'll purposely orient these coordinate systems a little differently. So ignore the left side for now. These are the element coordinate systems for each element. We know by default that the material coordinate system is parallel to the element coordinate systems. So these are the current material coordinate systems. Now let me turn that off. Let me go back to the material orientation field. Let me select this face. Let me select this coordinate system. And what am I saying here? I'm saying take every element associated with this face, align the material coordinate system so that the x-axis is aligned to this x-axis, which is this red axis here. So when I go back here, all the material coordinate systems are now parallel to each other. They're all aligned to each other. Now what I'm doing here is I purposely have different 0 degree directions, if you will. The material coordinate systems are different. This one's running horizontally here on the left, but here on the right, it's at an angle, if you will. Let me close this. Let me export this now, and I'll call this Model B. And save. Export. And let's go ahead and run this with Nastran. Now let me move this side by side. Hypothetically, everything should be the same, right? And let's look at the analysis. Let's first make sure there are no errors in the F06 file. Okay, perfect. Now let's go ahead and make sure we get some external work results here. External work, where is that at? Oh, here it is. Okay, perfect. So this worked. Okay. So now there's one very different option here. Field 7 is by default blank. Field 7 defines how you orient the material coordinate system of that element. Before it was blank. So since it was blank, by default, the material coordinate system was parallel to the element coordinate system. So that's what we had here. But then this is what we did. We went ahead and set this. Hey, take these two different coordinate systems, 1 and 2, make the material coordinate systems parallel to these other local coordinate systems. So here on the right is the updated bulk data file. If you look at field 7, I think it was, field 7 now has an integer. This integer 1 is a pointer to coordinate system 1. That would be here. So this is a coordinate system 1. This is coordinate system 2. So we set for half of the elements approximately, force the material coordinate system to be parallel to local coordinate system 1. For the second set of elements, force the material coordinate system to be parallel to coordinate system 2. So now you see a 2. Now, let's look at the results. I don't know if I ran this. Yeah, I did. Let's now look at the results. I think before we were looking at the results for layer 3, which was this. And now let's go ahead and upload that bulk data file in the H5 file. And now what you'll see in a moment, you'll see that the direction of the applied stresses are now pointing in the same direction because we modified the material coordinate system. Okay, let's turn out the deformed shape. Let's go ahead and select the apply stresses. Let's put this here. Let's go ahead and turn on the 3, display the directions, and I think I changed the color. Okay, perfect. So we're looking at the same thing. We're looking at the sigma 1 stresses, the stresses in the y-axis of layer 3. For the original model, that was not modified, that was left as default. And for the new modified file, if you can see that the apply 1 stresses before are pointing in completely different directions. These stiffnesses are completely wrong in this first example. We realized that, hey, my observer, my material coordinate system, they were never modified. They were left to point in completely different directions. So then what we did is we went in Apex. We said, you know what? Take all the material coordinate systems and make them parallel to these different local coordinate systems. And this is the result. The sigma 1 stresses for this side are all pointing in the same direction. And then the sigma 1 stresses for the other side are pointing in this direction. Now, let's do one last modification. Let's go ahead and copy this here and here. So we're going to copy and create a third model. Let's go ahead and put that here. And I'm going to modify this 2. I'm going to make this maybe a 1. Save that, and let's rerun this with Nastran. Okay, let's go ahead and open a separate window now. Now what I did in that last edit, I said all the elements, all of their material coordinate systems are going to be parallel to only coordinate system 1. So you notice a moment ago, this set 2. So you can see it says 2 here. I said, you know what? Make all of these 1. We ran Nastran, so let's go ahead and upload the results. And now let's look at the results real quick. And we'll do this for layer 3. We'll turn on the direction. And so here's before and after. So this is layer 3 and 1. So you can see that after we made that modification, all the material coordinate systems are parallel. All of them are. So the one direction of this ply, they're all in the same direction. In the second model, we purposely had one side of the elements you be parallel to one coordinate system, and then the second set of elements on the right were parallel to a different coordinate system. So here I wanted to show you how to work with the material coordinate system, how to modify the material coordinate system. Now, I see a lot of students not know about this. And unfortunately, the results in most cases are wrong because of this one detail. they never got to this part where they were modifying the material coordinate system. So I wanted to create this video for you. Hopefully you realize the importance of this material coordinate system. I know some of you are going to create maybe aircraft. Some of you are going to create maybe ground vehicles for some of the what is it called? Formula FSAE, I think it's called. Make sure that you properly orient your material coordinate systems, so you properly define your stiffness and you properly are looking at your apply stresses. One other thing here, if we, I don't think we could. Right, I'll skip that for now. Okay then, so I think we're pretty much at the end of the video. Hopefully you found it useful. Remember, if you're working with composites and you do not know about the material coordinate system, stop. You're most likely configuring your example incorrectly. Go through this workflow, go through this video, understand the importance in the material coordinate system, and I promise you will get reliable results after you configure your analysis. Okay, so that's pretty much the end of the video rather. As always, thank you for watching the video.